Our next speaker, Kristin Tolle, will discuss the role of the private sector in harnessing big data in the environment. Kristin is the Director of Program Management in the Advanced Analytics team at Microsoft. During her 10 years with Microsoft Research, she launched and managed several major programs, including environmental infrastructure development, where she managed a team of program managers, developers, and testers to build the infrastructure and data management underpinning a suite of cloud-based environmental science tools. Kristin received a BS in Computer Information Systems from Boise State University and an MS in Management Information Systems and a PhD in Management of Information Science, Computational Linguistics, Medical Informatics from the University of Arizona. Kristin?
Thank you. And thank you for having me. I'm really honored to be invited to speak. The only person I actually missed speaking was my colleague Lucas, who actually I've been working with. He was also in our Environmental Science Services team working together. But about 7 months ago, I actually left our organization and I went to work for the data science platform team inside of the corporation. So I'm now a corporate wonk. But for the previous 10 years, I was in research. I'm finding it very exciting to be back there, but I'm very glad to be here with you today. And I'm really glad to be talking to you on this topic. Just to kind of give you an agenda of what I'm going to go on about. I'd like to just give you a very brief overview about Azure, because I am a scientist myself, and a data science in particular. I tend to speak in the words of case studies, so forgive me if I don't spend a whole lot of time on the corporate stuff and spend a lot more time on the science, because I am actually a scientist. So I'll give you an overview of that, and then I'm going to go into Azure. So the one thing I've just got a few key points that I'd like to make at the very beginning, kind of like at the beginning of Brad's talk, where he wants to have a few things really kind of settle in. The cloud is ubiquitous. It's everywhere now. We have 34 different access points around the world, and while that might be twice as many as our nearest competitor, those guys have half as many, and there's a lot of them. So the reality is that it is everywhere, that you don't have to be concerned about having access to it. The other thing is that the cloud is secure. At least I can speak on behalf of us. We have over 28 different security certifications that ensure the protection of the data that you would place with us. And then there's choice and flexibility. If you want to use a Linux VM, knock yourself out. If you're into using MySQL, go for it. If you want to run a WordPress blog on top of it, it can happen. So you don't have to abandon the types of tools and experiences that you're using today. You can keep using those tools. All you're doing is just handing over the security and operation of the infrastructure to somebody else. The other thing is that, and this is kind of critical to some of the other things that I'm going to be talking about later on in the case studies, is that it's got a very hybrid system in the sense that if you want to have your Amazon cloud talking to the Azure cloud, talking to another data source or another data center, that's okay. That's very easy to do and pin things together using something that I'll go into a little bit of a deeper depth later on called Azure Data Fabric. So you can even keep those things now. Just to kind of tell you this, Ruth was saying, why is she here today? This is why I'm here today. So while I'm no longer inside of our Microsoft Research organization, something Stephanie raised earlier is there's a very large gap between science, the government, and even other sectors of the private sector where people don't understand the tools that they have available to them for the processing of big data and doing data analytics. And so I've been tasked with moving into our product organization to help educate people on our suite of tools. But the thing is that these suites of tools actually are fairly common across different types of clouds. Some are, like we have a very deep analytics space, other clouds have other things that they bring to bear as well. But in our particular case, we have, I don't know if you can do a quick count, But there are 14 different technologies in my purview to train people on. And every single one of these is a service. It's not the infrastructure, it's not the platform or the operating system. It is an actual application running on top of the cloud that enables people to do advanced analytics. And so it's bridging that gap that's the function of my role. And now to get into my case studies, because that's what I like to do, talk about the most. So it came up actually earlier in Brad's talk. He was talking about Quasi and the Open Water Initiative. That's something I'm extremely supportive of. And one of the last research projects that I did while I was still in Microsoft Research was actually doing flood forecasting. And it was part of this thing called the National Flood Interoperability Experiment. It's not called an experiment anymore because we were successful. We were actually able to map together different federal data sources and be able to provide that to local people and local first responders, people who are actually going to be boots on the ground in the case of a flood, to provide better services to us when in a disaster type of situation. But even though I say this, I mean, really the challenge has been, being able to do this across boundaries. Like, I think that was another comment that came up. How do you actually calculate these things across boundaries? And so one of the examples and experiments I'm going to show you, we'll talk a little bit about that. But just a little bit more background. It's a spatial and a temporal problem in order to put this together. And the reason is because the USGS has this wonderful historical data on stream gauges. And that's very valuable for doing projections into the future. The Army Corps of Engineers tells us what our reservoir levels are at in real time. So you need to look at where's the reservoir at and how does that affect maybe even stream gauges downstream if you're doing analytics. And then, of course, the National NOAA, or the National Weather Service, and the Associated National Center for Atmospheric Research. These are the folks who actually do our weather forecasting and being able to determine how things are going to play out into the future. But the problem was that these things were not all mapped together. So that was the objective of this experiment, was to see how we could take these different types of data that were gridded at different levels, information coming in at different timestamps. For instance, USGS, some of the stream gauges report it every 15 minutes. Some of them it's actually every couple of hours. How you rationalize all that data, do interpolation, and try and get some really good accuracy with regards to doing flood prediction. And then, lastly, FEMA spent a lot of money doing inundation maps. How do you then map those prognostications over the top of that flood map so you can actually do things like what-if analysis in regards to what could happen in the case of a heavy precipitation? I already talked about the spatial and temporal aspects, so I'm going to kind of move pretty quickly. I also have a lot of slides, and I want to leave time for questions. But the architecture that we used was we took NLDP Plus, and we actually built out, processed the geospatial data, bringing that together. We then put all that information up in the cloud. We pulled in forecasts from the National Weather Service and the National Center for Atmospheric Research. The USGS data came in, and then we created a model using something called RAPID. I know there are probably a lot of you are familiar with this work. It's Cedric David, who was at UT Austin and now is at JPL, was the inventor of that particular system. But what it allows us to do is do real-time or near real-time analytics against this particular data. And he was really gracious. He came over to Microsoft Research and joined me to actually put that up onto the Azure cloud. Now, what's interesting about that is once you have it in the cloud and bringing this data together into a single data product allows you to do the kind of analytics you wouldn't normally be able to do because you're cutting across these different agencies for the data. But we were able to then create the flood data itself, do interpolation using Azure Machine Learning. And this allowed us to then do impact assessment at near real time. It wasn't actually real time. It took about 15 minutes to actually run the full model. But for doing that across, nearly 3 million river reaches, I think that's a pretty exceptionally short period of time. Of course, we used at that time the largest cloud configuration that was in existence. It's been surpassed now by us and others since that time. But at the time that we actually did this experiment, which was in 2015 at the National Water Center, it was the largest cloud configuration. And what this enables us to do, so I don't know about you, but I get these occasional alerts on my phone that said in King County there might be a landslide. that's about zero help to me. Dozens of people, unfortunately, in Osa, Washington, lost their lives because they got some kind of county notification. Not that their house might be buried under mud. So my phone knows exactly the path that I typically take to work. It knows what home is to me. It knows where my office is. And it can give me a different route. In the case of a first responder, it can help a first responder get to you when there's a road washout, rather than taking the risk of their own lives or risking not getting to you in a timely way. So that sort of local alert, like literally down to the cellular cell phone level, is something using some of the mobile analytics systems that we have is actually a viable outcome. And it also, like I said, doing the what if analysis, you can plan for things. Where will things be inundated? How do we prepare for a situation when we see an extraordinary amount of water? And I don't know if you know this, but I wasn't going to tell the story, but it's kind of a curious one. The reason why we actually did this experiment was we were down talking about droughts, and down in Texas at UT Austin talking to the Texas Water Quality Board. And that night that I was there, we had this huge flood, and it washed out 500 homes, and several people lost their lives as a result of that because a stream gauge failed to work properly. Emergency services were deployed, but then they were sent back because that stream gauge dropped to zero. So in places like Arizona and Texas, it's really actually feasible for a stream gauge to go from 15 feet to zero. That actually does happen in a 15-minute interval because of flash flooding, because the washes are basically sandy and the water just goes down into the ground or washes straight through. So it's, they thought the disaster was averted, but it actually turned out that stream gauge had failed. So one of the experiments we wanted to do is actually estimate. That's why we started doing the interpolation and estimation in between the stream gauges in order to predict those. One of the students who was working in the program, formerly a student of David Maidment's, he's now at UNESCO, helped also put some of the different types of metrics there because he was working on drought. He put soil moisture models and things like that in an Azure Web Service. You guys can actually hit this today if you'd like, or I can as well. I think I may even have it up. Or I can show you at the break, it depends. Or precipitation, and these are real time. He also reports this statistical analysis out to the side. I actually am running this, by the way, in the background. That's why I said I could flip to it, but I think for the sake of time, I won't do that. And just kind of blow that up. It calculates soil moisture, evapotranspiration, precipitation runoff, and temperature. So back kind of to doing the estimation of models. Although I'm only showing 3 models, and like Brad, I'm from Idaho. Well, he's from Arizona, but I'm from Idaho. So when we wanted to do this estimation, we used the Boise River. I think you heard in the opening, I graduated from Boise State University. I was born and raised in Idaho. So, of course, the river that means a lot to me is the one that runs through our campus. And even though I'm only showing 3 gauges on here, that's just because if I showed all the gauges that ran off the Boise River, it would look like a mess and it wouldn't be very helpful. But the reason I've chosen these 3 is that the blue and the green are one is positively correlated, the other one is negatively correlated. And using past USGS data, what I did is actually created an Azure ML. This is kind of getting back to something Lucas said about reproducibility. Azure ML is just a drag and drop UI where you literally pull the modules in. So I have my data, I get a module that says go get that data, brings that data in, and I drag it onto this workflow. Then I can hook that up to training, pick a particular algorithm. In this case, I used Boosted Tree. So I grab that algorithm, I train it, I test it, and then I have a result. And then off to the far side, it's kind of an eye chart. I'm sorry about that, it doesn't show up so well here. Is a R module, which in my mind is the lingua franca of data science, that actually does the visualization of that graph that you just saw. So, and just for your information, you can run native Python or run native R or Python up in these systems in a particular module. If you click on the module, it just gives you a little window for you to put your code. So you can see, so the cyan line there is the prediction of the red one. The red one is the actual, and cyan is the predictive value of this particular stream gauge, but we were able to repeat this across it. And then later we were able to repeat it in places where we did spot checking of levels for places where stream gauges do not exist. Of course, with some of the newer technology that's coming out, like the overbridge infrared ones, that are much lower cost than the regular stream gauges. These can actually be put everywhere. And as Brad was saying, the data that's coming from these sites is extremely good, and they tend to be very long-lived, and they're very valuable for doing this sort of calculation. So anybody could repeat this experiment because the data is really, really good. So the next step was to scale it up to the all 2.7 million reaches across the United States, and we were able to do that, and so now it's not an experiment anymore. It's now the national water model that you can get access to through the National Water Center in Tuscaloosa, Alabama. So next thing I'd like to talk to you a little bit about is another experiment, which is actually doing energy forecasting. So it's really important for utilities to be able to estimate in advance demand. And so what we can do is we set up this particular workflow in order to get data from 11 different regions in the New York State. Each one of them, this is kind of a much simpler case with regards to data, because in the case of the previous example, data was hard. In this particular instance, these different regions report data all the exact same way. But they're doing it constantly, so it's actually being streamed directly in. So we used a tool called Stream Analytics to be able to pull that data in from the different regions, stuff it into a SQL database. Once you have it in a SQL database, then you can actually do dashboarding where you can visualize that data and take action against it. And perform calculations. So in this case, I used the Azure Data Factory to actually pull in an Azure ML model that we built. And I'll show you this. I promise this is the only code that I'm going to show you today. So the data is rather large. But it's super simple. If you understand SQL, this is a SQL-like language called Scope. And it was designed for the ability to access data when it is in the massive type of scale. We actually built it for ourselves because of the type of data. One of the things you may not realize is, yes, you know, the government has a lot of data, but corporations like Microsoft, Google, we have huge data. Facebook, we've all got massive amounts of data. And it's really hard for us to do telemetry and query against it ourselves. So in order for us to process our own massive data, we created a system that would actually do that in a parallel and very high performance way. And such, it took a special language in order to be able to do that. But if you know SQL, you'll know this in a heartbeat. It doesn't take any time at all to do that. This is a little bit more of a complex model cutting across the different centers. So again, like I said, it's actually, we're pinging 3 different utilities, or sorry, not 3, 11 different utilities in the New York State area using an R script to actually gather that data in. Again, R being the lingua franca of data science. We do run it natively. And then once you have that, you can actually visualize, this is the data after we've consolidated it together using that workflow, which is, by the way, repeatable. It's really nice. You could store those modules off and repeat them over and over again, and then be able to replay them to do your science, or tweak them in ways to do your science. And if you find that you've gone the wrong direction with a hypothesis, you can always just roll back. But you can look also at the data. This is data after we've consolidated it together into the SQL data warehouse. And then if I want to deploy that and make that visible to others, it's really simple for me to just make it visible to anybody on the web through deploying it as a service. And then if I want someone to access it programmatically, all I have to do is give them this API key, and they can build that right into their program. And then they get constant real-time refreshes of the data from these different 11 sites. So Azure Data Factory, as I mentioned before, is kind of what allows us to bring data together. In this particular instance, I'm going to just show you how we step through that. So first thing I want to do is I want to set it up to schedule how often it pulls that data and brings it into the system and then writes it out to the SQL database. And then I'm going to do that for each of the different 11 data sets. Oh, I must have deleted that slide. Okay, well, again, this is the consolidated database. And then all I have to do is pull in that data through our Power BI, which is also another web service, to then create a live dashboard. And I'm going to try it. So I'm literally querying the utilities of 11 different regions right now in real time while I'm standing in this room with you. And I'm displaying the output from that directly in this dashboard. And not only, you can see the different utilities down here on the map. Oops, oh no. Shoot. Oh. I can see it.
We believe you, Chris.
You get a presentation and you should be able to get the screen.
Oh, that's great. Thank you. Let me just do that.
Ooh, yeah.
There it is. Yay! Okay, good. And if I want to drill into any of this particular data, like if I click on the capital of Albany, I can actually drill down directly into that data. You can see who's the big energy user. Unfortunately, again, kind of an eye chart. That would be Manhattan. And the rest of those lines is all the other places. So Manhattan uses more electricity than the whole state of New York combined, which I found really interesting when I was playing with this earlier today. But when I look back here, I can also look, so the orange line there is a projection of what the power usage will be over tomorrow. So literally, I've got my historical data that goes into creating a model. And also, the most important thing to me, just like with the NLD Stats website that I showed you, is reporting what the error rate is. So you can actually get an estimate. That's the red over to the far side. That actually tells you what the error rate is. So you actually know what the error rate is against the projection that I'm showing. But yeah, this is a live demo as well, using that particular system. Thank you, by the way, that worked really well. Now, if I can just get back into my slide deck, I can skip over I was afraid I wouldn't be able to show it, so I actually tucked in a couple of slides in case it didn't come through. So well, it's funny. I have been working in artificial intelligence for more decades than I care to admit. I calculated it the other day, and it was really a frighteningly large number. More than half my life, probably 2/3 of my life. I've been working in the space of what used to be known as AI. Then it became machine learning. Then it became AI again, and now actually has moved into this space called ambient intelligence. And it's funny because all along I kept saying, not worried, until we got to things like ambient intelligence. And the reason why that is because ambient intelligence, the difference between it and artificial intelligence, still both are AI, is that in one case, you're the person saying what the parameters are that are interesting. In ambient intelligence, it infers it for itself. So, and in the former type of AI, you're doing classification systems individually. You might be linking them together yourself dynamically. But in ambient intelligence, you could have tens of thousands of different classifiers, all using a survival of the fittest genetic algorithm in order to see which one of those systems survive. Anyone that's not doing a good job of predicting it just kills it off, starts up another process. And so it can literally really operates more like the human brain. So I'm a little bit nervous, Lucas. I wasn't nervous before, but I've gotten a little bit nervous.
No,
This is actually for what you hear it about in the literature is something called deep learning or convolution networks. That's what's actually driving what we think of as ambient intelligence. And it was first major success was actually in another project that I was working on. And boy, this is way far in my rearview mirror, but it was actually speech recognition. We had a really great period of time when I was studying machine learning, because it had already made that transition to machine learning because it couldn't get funded as artificial intelligence any longer, where we were doing really well. But at then some point, we started leveling off in the accuracy of doing speech recognition in this example. Then all of a sudden, deep learning came along, and now we start to see a huge improvement in speech recognition, even in voices that it's never heard before or languages that it's never learned before. So this is where that sort of convolution network has its advantage by spinning up the multiple classifiers and tuning literally for itself to get a higher accuracy of it. So the result of this is actually Skype Translator, which was, I think, the second to the last project I did before I left the research laboratory. which works really well where some person speaks in one language and it speaks to you in whatever language you would like. So maybe it's making our world a little bit smaller. Even further back in my history, but this is actually going to drive me towards the new project that I'm working on with a colleague called Andre de Vries, who's in our London office. So the Worldwide Telescope, and I was really pleased to see Ruth put up Galaxy Zoo because this is the data behind it. But you know, I'm glad this is still out there. It's out in the open source. It's public domain now. Everybody can have access to it. That's fantastic. But this is 2008 for me, so it seems like very ancient history. But the thing is that what we'd like to do now is maybe take those convolution networks and apply it to a problem where we just don't have enough eyes with a data set that somebody doesn't care about. That's what Jim Gray used to say. He used to say, nobody cares about astronomical data. He doesn't mean that people don't care about it. I mean, you can publish papers and people love it, but nobody's going to get their hackles up if it's out there publicly. So it was really the perfect thing to have out there as a data set. And once again, I'm so pleased to be revisiting my work and the work that we talked about on the fourth paradigm because it's, Jim was still very near and dear to my heart. What I want to do is actually really classify galaxy structures using neural networks and with R. And so it used to be that we thought that there were about 100 billion galaxies in the observable universe, but with Hubble Deep Field, that number increased to 200 billion. And now, actually, with the Hubble Ultra Deep, we find that there are 2 trillion observable galaxies. And so classifying these galaxies is a very hard problem. And Galaxy Zoo as a social effort can only get us so far. It can certainly give us some data that enables us to do classification of these large scales. But really, we need to turn this kind of problem, this embarrassingly parallel, difficult problem. This is a classic example of something to turn over to artificial intelligence. The galaxy shape, actually, the reason why we want to study is because it actually tells us a little about the evolution of our galaxy and helps us understand where we are in our own Milky Way, our own galaxy, and where we are in the lifetime. And actually, we're a fairly young galaxy because spiral galaxies are at one end of the spectrum. Then they go through things like collisions and events. And then when we get to the end, we start seeing these galaxies that have burned up most of their gas, and they're not creating new stars. So they tend to look more like blobs. We also know that through Galaxy Zoo that the shapes of these galaxies are dependent a lot on the black holes that actually live inside the center. So a little bit about artificial neural networks. Where they actually came from initially, this looks very much like the first one I ever created when I was a graduate student, is they're modeled after neurons. Literally, you have an input layer, you have hidden layers, and then you have a classification outcome. And back when we were just classifying one problem at a time, that's when I wasn't afraid. But these days, actually, computers can really see, and how they do that is by breaking up the problem. They can determine faces because they see eyes, or because there's other distinguishing characteristics like ears that help them realize that's a person, not a bicycle, not a chair. So that's actually what they do, is they sort of see what things are from that standpoint. The value of using the Worldwide Telescope data is that just completely random thing. One of the designers of the system, his name's Jonathan Fay. The office used to be right next to mine when I was in research. He had this idea, like, if you want to see a galaxy, you want to see it resolve. And it's going over the internet, you might be on a slow connection. So what he wanted to do is he wanted to break every image that came out of the Hubble telescope into its individual pixels. So he put those pixels and their luminosity and other characteristics about them, each image, in a SQL database. And then what he would do is he would randomly select data from that and then resolve. So if you actually go to the Worldwide Telescope, you see that sort of thing. It gets crisper and crisper and crisper, because what that's literally doing is it's the next query refreshing, the next query refreshing, the next query refreshing, and then you have a very beautiful high-resolution image at the end. But that was the purpose. And it's so funny because even with Skype Translator, the reason why we created that system was to do language preservation. So a lot of this unintentional research that happens inside of Microsoft Research, eventually becomes something like Skype Translator, which is something that the company can productize. But it's one of the advantages of being where we've been is that we have this. We don't just look at the hill that's ahead of us. We get to look at the hill that's beyond us and think about things, what I would call even unintentional research. So this unintentional side effect is that it perfectly maps to how a convolution network thinks about the problem. So there are different problems that happen in doing this kind of identification. There's rotation, scaling, and translation. So feeding that into a neural network is not an easy thing to do. So just like in recognizing face, what we do is actually we start to recognize the pieces of it. Oops, went too fast. The center of it and an arm out to the side as well. In order for us to do that classification. And thankfully for us, that data was already pixelized in such a way that it made it very easy to put it into a convolution network. And it matches a specific shape. It looks around the different image itself. And then it does, because of the nature of how it can do its automatic feature extraction, it actually generates the features sorry, one of my people worked for me. Oh, it didn't come up there, good. It does its automatic feature generation. And the other thing is that because these layers can be stacked very deep, I was talking about the hidden layers in the small neural network, convolution networks also can be stacked to multiple levels. And then you can do the classification by running these over and over and over again until they become extremely accurate. The reason why I want to talk about our server is that one of the odd things that under Satya is that Microsoft as a company has embraced open source. And one of the systems that we have embraced as a natural language that we want to support is actually Microsoft, or not Microsoft R, but R, and in particular our server. The reason what our server gives you over the standard CRAN R that I used when I was just doing it back for the water, for the flood interoperability experience, I was just using RStudio, and this is back in the day before we'd actually purchased a company called Revolution R. What they did is they actually created algorithms that would spread the processing across the different, across the cloud, so that you could actually get the parallel computing aspects and do big data with R very quickly. So that's why we actually leveraged it for this particular experiment, because when you're trying to process all of pan stars, well, that's a big data set. But you want to be able to do that fairly quickly. So the infrastructure that we had was we took the Sky Server data that we already had in a SQL database, and then we took that and put it up into a storage blob. We used Microsoft R services to actually do the feature extraction and put that into what we call a data science virtual machine. And just for those of you who don't know, we did come up with this really nice service where I, as a data scientist, if I want to do data science, I just take one of these data science virtual machines off the shelf, and it runs on Linux, and it has all of the different tools that I need in order to do data science, so I don't have to spin that up for myself. It's like having someone coming over to you and handing you a fully implemented workstation that has every tool that you could possibly need for data science on it, except in this case, you just spin it up as a virtual machine. And that we actually sent to a new system that we have. We actually are processing GPUs, which lend themselves very well to computer vision type applications, but it was one of our N series machines, which is interestingly much larger than the machine that we use for doing the flood forecasting. But image recognition is an expensive process. So we ran the images through about 3 times 100,000 images. There were 8 layers in the particular network that we used. The different weights to compute it were about 176 features. And then it took us about 2 hours to compute all of the pan-stars data with an overall accuracy on 88% for the training data. Unfortunately, its predictive capability, it's not that great. But this is a first attempt. And just like the flood experiment, wasn't magic the first time. It is something that we'll continue to investigate. But mainly, really, the exercise for us was just to see if we could get all that data up there and perform it. And now we'll start working on the refinements to make it better than 55% accurate. And just in a shameless plug for my future work, this is an article that I just came out with. So I also, like Lucas, think about, and I've heard this come up several times today, which is what sort of emboldened me to put this up here. Built Environment is a new book that's, or magazine that's just come out. And my co-author, Harvey Miller at OSU, and I talked about how you take things like Geiger LiDAR, which, by the way, if you want to talk about high accuracy, and a lot of the utility companies have this data, by the way. We're talking, they have visual data that's at 30 points per meter. Very, very high resolution data over areas. Now, if you ran that over the top of a city, and then you start capturing the building information, and you start capturing the utility information, and then you start capturing that with the individual on-the-body sensor networks that exist, and you bring that all together, what the objective that we're trying to do is create environments, built environments that actually help us become healthy, live healthier lives inside of the civic places that we are, inside the cities that we live in. And so, in conclusion, really what to sort of wrap this all up in a nice, neat little bow, is the objective really of what we're trying to do here is sort of transfer science out of the worrying about getting their cluster set up, worrying about making it secure, worrying about, updating the operating system, worrying about providing people with access, but literally sort of pushing that down the stack and keeping instead the scientists out in the field, working on the science, gathering the data or gathering it from devices, bringing that together, transforming it really quickly, being able to remotely monitor processes, bring that down, do things like the planning and mitigation I talked about for the flood forecasting, but even for, you could think about this for all kinds of things, droughts as well. And then enable this to be able to be done across the globe, so bringing in data sets that are broader than the ones that we have, and then pushing that data back out globally so that we can take corrective action anywhere at any time. So that creates a circle that then goes back and that drives, fuels the scientific work that comes after it, because then they're working from a place of knowledge. And so that's it. Thank you very much.